Here we have an example of normal tangential coordinate system. So in this problem, we have a package which at x equal 10, based on the reference given, x equal 10 feet, reaches a speed of 20 feet per second traveling along a curved path, whose profile is given by that equation, y equal 1 over 24 x squared, basically a parabola. So what's given is that the speed is, so given that velocity at that instant is 20 feet per second. And we have one other piece of information that at that instant, the speed is increasing at the rate of 6 feet per second squared. The rate of change of speed, dv dt, or v dot, is actually tangential acceleration. And at that instant, that tangential acceleration is given to be 6 feet per second squared. So by that we mean actually this guy. So this is, if this is our t-axis, we know that there is a component of tangential acceleration like this, and that would be 6 feet per second squared. What we want to find at this instant, at this position, x equal 10, is the magnitude of acceleration. Magnitude of acceleration. So we know that magnitude of acceleration is part tangential, so at squared, plus the centripetal or normal acceleration squared. So whenever an object travels along a curved path, it generally has a tangential, which is tangential acceleration, which is rate of change of speed, and a normal acceleration, which is centripetal acceleration. Now normal acceleration, so we already know a sub t, right, is 6 feet per second squared. The normal acceleration has to be calculated based on v squared over rho, so is equal to v squared over rho. We already know the velocity is 20 feet per second at that instant, but we don't know rho. So for these type of problems, let me erase this. How do we find rho? Rho is determined actually whenever you have profile of a path. Rho is determined based on this equation involving first derivative and second derivative. So 1 plus y prime squared, then the whole thing raised to power 3 halves, divided by absolute value of the second derivative, y double prime. And this has to be calculated at that particular position that you want to find the radius of curvature. So this will tell us what the radius of curvature is at that instant. So let me go to the next page and we start doing this. So we already know that the reference, the profile is y equal 1 over 24 x squared. So we need y prime, which becomes 1 over 12 x, and we need y double prime, which is 1 over 12. But we have to go ahead and evaluate this y prime, which is actually the slope at x equal 10. So that becomes actually 5/6 when you plug in 10 over 12, 5/6. So let's go ahead and calculate rho. So according to the formula I had in the last page, 1 plus y prime remember is 5/6 squared, then the whole thing in the numerator, in the bracket raised to power 3 halves, divided by absolute value of 1/12. Absolute value of 1/12 is just 1/12. So if you go ahead and calculate this, rho comes out to be about 26.47 feet, roughly. So now we are ready to go ahead and calculate normal acceleration, which is v squared over rho. Remember, velocity was 20 feet per second at that instant, and I just calculated rho. So this happens to be about 15.11. So this is the centripetal acceleration in feet per second squared. So now remember, if I take the normal acceleration and tangential acceleration and square them, remember tangential acceleration was given, the rate of change of speed, 6. and we just calculated the centripetal or normal acceleration, right? So go ahead and find the resultant, and that would be the magnitude of acceleration, 16.3 feet per second squared. So that's the answer, magnitude at that instant. Just show you quickly what's going on here. Let me again erase this. So look, this is the tangential axis at that instant, and this is the normal axis pointing toward the center of curvature. So at this instant, we just determined that, or this was given, the 6 was given, that was a sub t, right? And we just determined that the normal acceleration is about 15.11, right? So the magnitude of these two, the one that I just calculated in the other page, is this blue arrow, which came out to be 16.3. That becomes the magnitude of acceleration.